In this video, we're going to apply our understanding of stationary points in order to find the maximum or minimum of a certain quantity. We'll start by introducing the overall framework we're going to be using for both TEC-free and TEC-active, and then we're going to apply those frameworks to some key questions. For those who don't know me, my name is Chris Iannazzoni. I've been tutoring for around 2 years now, and I make these videos so that VCE students can do the best they can in math methods. With that out of the way, let's get into it. In the vast majority of cases, the maximum or minimum of your quantity is going to occur at a turning point. With that in mind, there's only a few things you have to actually do. First, you need an expression for the thing that you're trying to solve. You can't maximize area until you have an area equation. From there, you'll just find a derivative and then set derivative equal to 0. The reason why is because all stationary points can be found by setting derivative equals 0, because all stationary points have a gradient of 0. Sometimes this will give you more than one solution. With that in mind, you could use the double derivative test in order to figure out which of those is the maximum and which of those is the minimum. Although we will see a few ways in which we can circumvent that. From there, once you have that x value, you're just going to sub that back into the original function to obtain the maximum value of that thing. If it was an area equation, then you sub in your x value to achieve the maximum area. TEC-active is significantly faster. You can actually skip all of that derivative stuff and just use the fmin or fmax functions on your CAS. Here's what it looks like on the TI Nspire, and here's what it looks like on the Casio. So, our goal is to find the value of x which maximizes the area of this shape. So specifically, we're looking for the x value, not the actual maximum area itself. Step 1 is to just find the equation of that thing we're looking for. We can't maximize area unless we have an area equation. The shape that we're trying to maximize is a trapezium, so we're going to use the area formula of a trapezium, where A, B, and H are depicted on the diagram. With that in mind, we can see that A is going to be x and B is going to be 3x, since there's 3 of them. H, however, is a bit trickier. For now, we're going to isolate that triangle. What we're going to realize is that we actually have enough information to create a Pythagoras equation. Once we do that, we can actually rearrange for h, thus getting h purely in terms of x. Now that we finally have a, b, and h, we can just sub that back into our area equation and simplify. So that's step 1 finished. We have our equation. The next step is to find the derivative of that function. Our function is a product of 2 terms, hence we're going to use the product rule to find its derivative. So we figure out what u and v are, and then find the derivatives of each of those. Now that we have all those terms, we're just going to plug those into our product rule equation, and then just simplify. Now that we have our derivative, we're going to set the derivative equal to 0. Again, the reason is that any stationary point, maximum or minimum, is going to have a derivative of 0. So if we solve where the derivative is 0, we're going to find the x-coordinates of those stationary points. The fastest way to solve this would be to multiply both sides of the equation by the root term. That way it's going to cancel it out in 2 separate places. From there, you just have a quadratic. This one can actually be solved with algebra. Just be sure to cancel out that plus minus because negative lengths don't actually exist in these application style questions, so only the positive root will be applicable. If we instead wanted to find the maximum area, not just the x value that gives us a maximum, then all we're going to do is take that x value that we found and then sub that into our area equation. Not the derivative equation, but the area equation. And when you do that, you're going to get 100 units squared. If you were to do this TEC-active, then you could skip all that derivative stuff and just use the fmax equation. Here's what it looks like on the TI Nspire, and here's what it looks like on the Casio. The syntax is the same for both. You just write the function and then comma x. Alright, so we can do areas of shapes now, but how about this kind of question? This kind of shape is actually bound by a curve, where the coordinate of b is set by x, and the line that is vertical from that sets the coordinate of p. Those 3 coordinates together form a triangle. Well, step 1 is to find the equation of the thing we're trying to maximize. In this case, it's the area of the triangle, hence our starting equation is going to be half base times height. From here, just like before, we need to get our equation purely in terms of x. So first, let's look at the base. In this case, the base is spanning all the way from -1 to x. Hence, the total length of our base is going to be x plus 1. Now for the height. The height of the triangle is going to start from 0 and end at y, but that's just interchanging h for y. That's not quite good enough. This is where the fact that it's bound by a curve starts to matter. That intersection point of P, being the xy coordinate, that y value actually belongs to the curve of that semicircle. So if y is the square root of 1 minus x squared, then we can replace that letter of y with that square root term, thus finally getting everything in terms of x. Now that we have all that, we're just going to plug that back into our area equation and then simplify. Next is to find the derivative of this. Just like before, the derivative is going to be found using the product rule because it's again a product of two separate terms. So we're going to determine what u is and what v is, and then find the derivatives of each of those. Once we have all of that, we plug it into our product rule equation and then simplify. From here, we're going to set our derivative equal to 0 because once again, we're trying to find a maximum, which is going to occur at a turning point. The fastest way to solve this one would be to multiply both sides by the square root term. That's going to cancel it out in two separate places, and it's going to give us a quadratic to solve, which this one here would be best solved using the quadratic formula. You could solve it with a factorization approach, but that can be kind of hard to do in a tech-free environment when you have limited time in your SAC. At this point, we have two possible solutions for our x value. So we're going to move on to step 4, which is to figure out which of those is actually the maximum. Now, we could do a double derivative test here, but to save a few lines of working, what I'd recommend doing is trying to think about which of those x values actually makes sense for it to be the maximum. If we had chosen x equals -1, that would put the b coordinate there, right overlapping a. Under those circumstances, you have no triangle. It's just effectively a dot right there. However, if you put your b coordinate at x equals 1/2, you can see the triangle is much more respectable. This is going to be our maximum. So now that we know that x equals 1/2 gives us the maximum, we're going to take that x equals 1/2 and then shove it into our area equation. Once you simplify, you'll get your maximum area. Once again, if you have the CAS, you can skip all that derivative stuff and just use the Fmax equation. It's actually doubly good because now you've only got one x value to worry about instead of comparing two different ones. So you're just going to take that x value of 1/2 and then chuck it back into your area equation, and well, the CAS will simplify that for you. And on the Casio, even better, because the Casio gives you both the x and the max value at the same time. Here's a new take on the question. This time we want to find an angle x that maximizes area. This only feels different because we're working with angles, but fundamentally we're still just going to grab our area equation and then get it purely in terms of x. So let's start with that. This is a trapezium, hence the area equation is going to be a plus b over 2 multiplied by h, as depicted in the diagram. A is pretty obviously just p, they're labelled in the exact same spot. When it comes to solving the other terms, we're going to have to work a little bit harder. Oddly enough, it's actually easiest to solve h first. We're going to do so using SOHCAHTOA once we block out everything else but that right-hand side triangle. Specifically, we want h, and based on where x is located, h would be considered the opposite to that angle. From there, we know that p is the hypotenuse, hence, if we have opposite and hypotenuse, that gives us sine is equal to h over p. All we're going to do from here is rearrange for h. Now, when it comes to finding b, it's not so bad. It's just going to be one copy of A and then two copies of C, again as depicted on the diagram. When it comes to finding C, it's also going to be done using SOHCAHTOA, but this time we're using the cosine because we have the adjacent and the hypotenuse. Once again, B is just 1A plus 2 C's, so we're just going to sub in our values for A and C, and that's going to give us B. So we're just going to put all that into our equation and simplify. If you have the CAS, then just let the CAS do that. This actually was a CAS question, so at this point we can pretty happily just use the Fmax equation. So we're going to put in our function, comma x, that's going to give us the x coordinate as required. Just be sure to put a domain on your Fmax, otherwise you're going to get infinite solutions. Restricting it between 0 and pi over 2 makes sense because that would be between 0 and 90 degrees. This is actually where the question ends. We wanted the angle, not the actual maximum at that spot. If you did want the maximum at that spot, you would just sub in your x value. Let's change things up slightly. This time we're going to find a minimum. specifically a minimum length. Step 1, find our length equation. If you want to minimize length, you first need an equation that describes length. Length is just a distance, so we're going to start with our generic distance equation. What we're going to do now is figure out what our points are. The origin is clearly a point, but P is a little bit harder to justify. The point P is told to us as just some point that exists on that linear equation. So we're actually going to keep it generic. The only thing we're going to do is rewrite y as our linear, so we get everything purely in terms of x. From there, we're just going to plug in those 2 points into our distance equation and simplify. Next up, we have to find our derivative. Firstly, I'm just going to rewrite the root so that it has a power of a half instead. That makes it a bit more obvious that we're using the chain rule instead. With that in mind, we take the inner and take it out of the function and find its derivative. From there, we rewrite our function purely in terms of u and then find the derivative of that. Those 2 derivatives we just found are going to multiply together, and that's going to give us the result of our chain rule. Just be sure to replace u with what it was before we did our substitution. Now that we have our derivative, we're going to set it equal to 0 and then solve. This might look complicated, but once you realize you just got to multiply both sides by the denominator, it just becomes a linear. And so you solve it like you would for any other linear. From here, we're actually going to deviate a little bit from our procedure because we're not actually trying to find a minimum or a maximum. We're trying to find the coordinate of P. Since we just found our x coordinate, we can sub that x coordinate back into the linear equation to get the corresponding y coordinate at that spot. And once you have an x and a y coordinate, you've solved your question. If you did want the minimum distance, then instead of putting it into the linear, you put it into your distance equation and then simplify that. That will give you minimum distance. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool. You should check it out. I'll see you there.